data that we have here show the volume of an injected fluid as a function of time. And what we want to be able to do is take these data and determine what the flow rate of the injected fluid is as a function of time. So if we have volume as a function of time, then the flow rate, the volumetric flow rate, is just the derivative of the volume with respect to time. So there are a couple of ways that we could do it. One way would be to just recognize that the derivative is the slope, and these squares show the measurements that we've made, the volume that we've measured at different times. And so one possibility would be to just take the slope of the line between these points as the derivative, and that slope then would give us the flow rate. And so there would be a couple of ways that I think we might be able to come up with to do this. And let's just say, as an example, that we want to get the slope at this point that we'll call it T2. And I'm going to do that because I'm going to use this point here, and I'm going to call that T1. So time 1, time 2, and the time at this point right here, that would be T3. And similarly, we'll have, this would be volume 1, volume 2, and volume 3. So each one of these 3 points is characterized by a volume and a time. Okay, and so I think what we could do is say that the flow rate at time 2 could be determined by that slope. So if we say that, it would be Q at 2 would be V2 minus V1 over T2 minus T1. That would be one possibility, but of course we could also use this slope here. And if we did that, we would say that the slope at time of 2, Q2, would be equal to V3 minus V2 over T3 minus T2. And then another possibility would be to say, well, if I want to get the slope at this point, a better approach might be to use both that point and that point, the two flanking points. And if I got the slope between those 2 points, it would be that line. And so I could say that Q2 would be V3 minus V1, which we recognize to be that, divided by T3 minus T1. Okay, so those are 3 different ways that we can calculate the flow rate, the derivative at this point T2. And we're doing it just using the data itself. Okay, so these are finite difference approximations of the derivative, and they have different names. This first one that we wrote uses, we want the derivative at point 2, and it uses measurements at point 2 along with the measurements behind point 2 or at T1. So that's called a backward difference. And the next one uses the data at point 2 and at the point in front of it, so that's a forward difference. And this last one uses the points on either side, and if these are equally spaced, and this point here, T2, is right in the middle, then this would be a centered difference. Centered finite difference. Okay, so those are 3 methods that I think we can just get, I think they just make sense intuitively based on kind of just an intuitive evaluation of these data. Okay, so here's a look at what we've just done. The blue points are the data, so we've taken the slope between those points and those 2 points and those 2 points and so on. And then what I've done is plotted the slope here as these boxes, kind of a histogram looking thing. And if we go over here to the right side, you can see the scale. So during this first interval from 0 to 5 days, the flow rate is 70 liters per day, which would be the slope of that line. Okay, and then you can see that the flow rate is decreasing with time as this curve kind of flattens out. So here are the three methods: the forward, backwards, and center differences. And what I'm doing is writing the equations that we saw on the previous slide here in a little bit more general form. What I had before was Q at point 2, and that was equal to V at point 3 minus V at point 2 over T at point 3 minus T at point 2. Okay, that's what I had for the forward difference, but now what I'm writing is Q at N equals V at N plus 1 minus V at N, and so on. And so the idea is that you can fill in any number here with N. It's just a variable. And so what this does is it takes the specific example that we saw on the previous slide and extends it to essentially any pairs of points that we would want to use. The one exception would be that with this forward difference, if we want to do the forward difference at this point, we need to have this point that we would use. And so the problem with that is that it works for all the points except the last one. If this is our last measurement, then we can't use this forward difference approximation because we would need another point out here, so it just isn't available. So these are the backwards and center differences written in these general ways where the subscript is a variable. So these finite difference approximations of the derivative really are a kind of a special case, or they're certainly related to the definition of the derivative. And this is what you'll find as the definition of the derivative if you look it up in your calculus book. What it's saying is that if you have a curve like this one right here, and you put a point on it there and there, that would be right there. That's f at t plus delta t. So that point right there would be f at t plus delta t. And right here, that point is f at t. So we subtract those, divide by delta t, which is right here. And that's essentially this finite difference approximation that we saw in the previous slide. But what it says now, the definition of the derivative, is that if we do this and we take the limit as delta t goes to 0, then that gives us the actual definition of the derivative. Okay, so what we're doing then with the finite difference approximation is that we're somewhat relaxing this requirement. So we're not letting delta t actually go to 0. We're just saying delta t is going to be some small number. It's an actual finite increment, but it's a small one. And if that's the case, then this expression here becomes a reasonable approximation for the derivative. That's essentially what we're up to. Now, one of the things that we want to do is see how well we're doing. These finite differences are approximations by definition, and so we want to have some measure of how much of an approximation they are. So there are really two ways that we could do it, in two simple ways. This is called the absolute error, and it's just the absolute value of the approximate value saved by a finite difference minus the exact value, assuming that we would know that. So the absolute error, and then there's the relative error, which is just the absolute error, the approximate minus the exact, divided by the absolute value of the exact. Okay, so the way this is going to work is this is the difference, or this would be like a residual or a difference between the approximate and the exact, and then we're scaling that to the exact value. So this is like a fractional value. The approximation is expressed as a fraction of the exact value, and we make that a absolute value, because now when the approximate value is greater than the exact, this is positive. So the relative error is positive when the approximate value is too high, and it's negative when the approximate value is too low. Okay, so what I want to do here is try this out. Here's this index n. So we've got these 6 different terms, and then that's t. Yeah, it looks like the formatting got a little bit messed up, but there's the time in days, and here's the volume in liters. And what I want you to do is calculate the forward, the backward, and center differences using these data. And these data were used with the curve fitting method, where we fit these data with a curve, and then we took the derivative of that curve, and that gave us a possible way of estimating, or an alternative way of estimating the derivative. And so those data are given right there. And so what I want you to do is calculate the derivative and put the values in here, and then assume that this column is the exact value, and calculate the errors, the relative error of these data compared to this exact value. Okay? So go ahead and do that, and print off this table and fill in these values, and then get that all worked out, and then you can test yourself and compare your results to the values that are the correct ones, which I'll give you in an accompanying video.